In this video, we discuss fluid dynamics. And up to now, we have considered fluids that were at rest. And so in this video, we consider now fluids that are flowing. Before, we need to introduce a couple of definitions. So the first thing is the notion of an ideal fluid. This is a fluid that we will consider incompressible and with no viscosity. And the viscosity is the internal friction of a fluid. So some fluids are very viscous, for example, syrup, and those kind of fluids tend to resist the flow. And water is not very viscous and compared to syrup, and so it does not resist the flow as much as syrup. Next, we have the idea of a flow line. Right? A flow line represents the path of an individual particle. So think of this as the line that represents the trajectory of a cannonball. Now imagine that the cannonball keeps shooting, then all the balls will follow the same trajectory. And this is what we call a steady flow. Right? This is when the flow lines do not change with time. Now, make sure you don't misunderstand this. Right? The word steady here is for the flow. It's not for the particles. Right? The particles are not steady. They are moving. But the flow lines are the ones that are steady. Now, a streamline is a curve whose tangent at any point is in the direction of the fluid velocity at that point. So if the flow is steady, the streamlines are the same as the flow lines, and they do not change with time. But if the flow is not steady, then the streamlines and the flow lines are changing with time. And so in that case, the flow line is following the same particle trajectory as a function of time, but the streamline is taking a global view of the flow, looking at many particles at the same time, and the line that connects the velocity vectors of these particles is the streamline. Now, because in this class we only consider steady flow, then streamlines and flow lines are always going to be the same for us. A flow tube is a tube that is bounded by flow lines, and it is something that we will use because when the flow is steady, then all the particles in the tube move inside the tube. And a laminar flow is a steady flow in which the adjacent layers of the fluid slide smoothly past each other. Essentially, this is saying that the flow lines are almost parallel to each other. This is in opposition to a turbulent flow, which is irregular and chaotic. An example is the flow of smoke. Right? At the beginning, near the candle, it is laminar, and then as it goes up, it becomes turbulent. Another example is the flow of water from the faucet. At low speed, the flow is laminar, and you can see like water is transparent even, but at high speed, it is turbulent. So again, as I said, in this class, we will only consider steady and laminar flow. And so for such flow, then we can derive a relation that is called the continuity equation. And so let's consider a flow tube. On the left side, the section of the tube is A1, and the velocity of the particles is V1. And on the top side, the section of the tube is A2, and the velocity of the particles is V2. Now, let's consider the particles that are at the section A1. During a time dt, a certain amount of particles will flow across A1. Since the velocity of these particles is V1, during a time dt, they move by a distance equal to V1 dt. And so the volume flowing across A1 is given by dV1 equal to A1 V1 dt. And so we can calculate the mass flowing across A1, and it will be given by dm1 equal ρ1 A1 V1 dt. We can do the same for the particles that cross A2. Those particles have a velocity v2, so during a time dt, they will move by v2 dt. And so the volume flowing across A2 will be dv2, which is equal to A2 v2 dt. And the mass flowing across A2 will be dm2, which will be equal to ρ2 A2 v2 dt. And now, because it is a steady flow, then no fluid flows in or out of the sidewalls of the flow tube. Right? The flow is steady, so the particles that enter across A1 follow the same path as the previous particles, and eventually they will exit across A2. Right? No particles will cross the walls of the flow tube. And so this means that the mass that enters across A1 is equal to the mass that enters, that passes also across A2. Right? So dA1 is equal to dm2. And so we can write that ρ1 A1 V1 is equal to ρ2 A2 V2. And this is known as the continuity equation for a compressible fluid. Now, if the fluid is incompressible, then the density will always be the same. And so we can simplify ρ1 equal ρ2, and we obtain that A1 V1 is equal to A2 V2. Another way to say this is that the product A1 V1 is a constant in a flow tube. And in fact, this product represents the volume flow rate. As you can see, we have dV is equal to A times V times dt. And so dV over dt is equal to A times V. Now, let's discuss the continuity equation for an incompressible fluid. Right? You see that if the speed increases, then the section has to decrease so that the product AV remains constant. And so you can see this by looking at the stream of water from a water faucet. Right? As the speed increases, you can see the stream of water gets narrower. And so V increases, the section A decreases. But keep in mind that this is only true for incompressible fluid. If the fluid is compressible, then it is the product ρ times A times V that is constant. An example of this is a traffic jam. Right? Traffic is like a compressible fluid. So when the section gets narrower, the speed does not increase, it is the density that increases. In fact, if traffic would be an incompressible fluid, then the speed would increase when there is a narrowing. Now, let's do a quick example. Let's say that you have a pipe with a radius R1 and a flow speed V1, and the pipe is connected to another pipe with a radius R2, and the pipe goes up by a height h. And so this could be a water pipe below your house that is servicing water in your kitchen, for example. And so what happens to the flow speed V2 if the radius R2 is half of the radius of R1? So R2 is half of R1. So the cross-section A2 will be a quarter of A1. And this is because the cross-section goes with the square of the radius. And because of the continuity equation, then V2 will have to be 4 times V1 so that A1 V1 is equal to A2 V2. So again, you see that if the cross-section decreases, then the flow speed increases.